can.
Okay, I assume everyone can. So I'm a statistician and I work with Terry Peterson and Ken Aho on model selection quite a bit. And so this is just sort of an overview of model selection with just a few comments related to health physics. So it's a broad view of how we look at things. This is an example of just the sale modeling trying to predict the price of a home based on some variables. And if you'll notice the data, it's real data. And one of the characteristics is it has a lot of points that seem to fit the model well, but a few that are very unusual. And so we're going to look at cross-validation, leave one out, cross-validation, and information criteria as methods of deciding which of several models fit the data, and look at how they're related to each other. And so I just picked 4 models. And I say the models, I want the model which will make the best future predictions. And later on, it will become obvious that exactly what you say you're trying to do affects how you want to do the selection process. So the first thing I'm going to look at is a very standard thing, the idea of data splitting. The first time I saw data splitting was in a machine learning class in the 80s, and statisticians picked up on it. But in this case, you choose 700 observations as a training set and 357 as left out for validation purposes. This works great with large data sets, which we don't see in health physics very much, but that's ideal for this. And then you just fit the models. These are 6 runs in which I found R squared for each of the 4 models for the training set and for the validation set. And in this case, it just turns out, we'll look at this more closely later at some anomalies in these numbers, but it looks like area and age are important, and number of bedrooms and area alone are not very good. And so you would have the idea of which of the 4 models seem to be best for making future predictions of housing prices. Now I want to talk about a completely different way of thinking about things, a curve fitting, a way of thinking about curve fitting in general, or model fitting in general. It's called the bias variance trade-off. And we know that when we try and fit a curve or a model to data, if we underfit, we're going to produce models that are too simple and can't really capture the complexity. But if we fit models that are too complex, we're going to overfit, and we're going to fit to specific idiosyncratic characteristics of the data. And so this idea of overfitting and underfitting and balancing these two things can be thought of as the bias variance trade-off. Simple models have bias in them. Overfitted models have too much variance in them. And as an example of this, I'm going to do a simple curve fitting exercise I often have as a homework for my students. Well, first I'm going to talk about the information criteria itself. I'm going to now talk about Akiaki's information criteria and tie it back to how it's related to data splitting. And in the general form, AIC is -2 times the log likelihood plus 2p. For small sample sizes, with the normality assumption, you can have a correction on the far right that really penalizes complex models. But that, of course, that penalty goes away as n grows to infinity. For SAM, SAM2, the specific calculations are given there. And in SAM2, what happens is you have a variance associated with each compartment, and you have, of course, all of your transfer rates, and however many you choose to optimize, how many variances you choose to optimize, and however many transfer rates you choose to optimize sum up to what P is. The things that are optimized rather than fixed at known values are P. And so for simple regression, of course, it's a very simple calculation. It reduces down to something very simple because there's a lot of extra simplistic assumptions. So for this model fitting exercise I'm about to do, I'm going to use the AIC at the bottom. And what I'm going to do is I'm just going to simply show you how AIC works. We have a sine function and a bunch of random noise around it that generated the data. And then I'm going to try and use AIC to fit a smoother to the data that works reasonably well. And so AIC in this form is really just involves the sum of the squared residuals. I'm going to apply in the language R something called smooth spline, which is a, a spline smoother that can have variable roughness. We're assuming the errors are normal and have equal spread, which they do. And for any use AIC, you must be able to estimate P, and this smooth spline in R uh, gives you an estimate of P. So P controls the smoothness. If P is small, it's a very smooth curve. If P is large, it's a very rough curve. We're simply going to fit a bunch of values of P to this data without knowing what function generated it and see if AIC has any luck at finding a good fit. So here are 4 choices of P. You'll notice that when P, the solid line is the true model, the dashed line is the line that smooth spline is fitting to the data, and P is the roughness. And you'll notice at P of 5, we're not rough enough. We're not really capturing we're not able to bend enough to capture what's going on. At 8, we're doing pretty well. But as we go to 12 and 16, we're getting into a range where we're overfitting specific characteristics of the data that have nothing to do with the underlying function that produced the information. So I often find myself making charts like this. I've got the sum of the squared residuals, the values of P for roughness. And it turns out that AIC is doing an excellent job of finding what is about the right model for future prediction. And so that's sort of how AIC works. And it's one way in which you can decide how to decide between over and under fitted models. Another approach is known as leave one out cross validation, which I think many of you may have heard of. It's very simple. It can be done algorithmically. You just simply drop each observation, fit the model with that observation left out, and compute a residual associated with that. And you just normally pick the model with the smallest overall residuals. It's a very straightforward method. And it works for small data sets where data splitting is not practical. Data splitting for small data sets is really kind of touchy. Well, it shouldn't be hard to imagine that leave one out cross validation and data splitting are very similar in their reasoning. And so that's probably not too surprising. However, what most people don't know is that, or what many people don't know, is leave one out cross validation is considered to be asymptotically equivalent to AIC. Stone in 1977, as referenced at the end of this presentation, was the first one to show this asymptotic relationship. In other words, what he argues is if you have several candidate models and you rank them based on leave one out cross validation and you rank them based on AIC and the sample size is large, they rank the models in the same order. And I also have a sort of in my time series book in an appendix, I also have sort of an argument that's more just simple algebra that says more than that you can transform AIC to an R squared type value and kind of come up with a more close matching of these two values. So what you'll find widely in the literature now is that data splitting, leave one out cross validation, and AIC are roughly equivalent to each other. So whichever one of these you like, you should be aware that if AIC is easy to calculate, even if you're convinced one of these others is better, AIC is something you can calculate very quickly as a back of the envelope calculation to see where things stand. However, I think you'll find with experience that that these things turn out frequently to be the same. I mean, for a period of time when I was working with Sophie St. Hilaire on some cancer data, we would independently do model selection over the course of a weekend, and she would use R squared predicted, which is leave one out cross validation for model selection, because the software we were using calculated it directly. And I would use AIC, which required some extra calculations, and we'd always be getting the same models. So that's really, they're very similar in their purpose. When we go back and look at this data set, I know it's very busy with lots of values here. What we find is data splitting seems to produce some very counterintuitive results. I mean, if we just focus on the first model and they all of them have the same characteristics, the
Morning, Scott.
Yeah.
Hey, Scott, this is Joe Guido. How are
Hey,
you?
Joe, I'm doing well. How are you?
All right, all right. Just, not much has changed here. Well, as you know, we just.
I just texted him to tell him he's not muted. I'll try again.
Yeah, I'm hearing a lot of other voices right now. Okay. Yeah.
Normal stuff.
So anyway,
I have a question about Pinellas, and I just thought, since you sent the last email on this, I'm working on an SEC petition for this, so I think it's like the 5th or 6th.
I think that's being picked up. Can we get somebody to mute that, please?
What's the probably line issue here, or should I talk to Brian? On their record.
Yeah, really, Brian's going to be the person to talk to. But the bottom line seems to be that we don't appear to be getting all their records.
Is this a new issue, or is this a no longer appear to get the records, or never, you know, like now, all of a sudden we found something in the SRDB, which indicates, hey, there's a lot more out there than they could give us.
I'm hoping.
I think we got to fix it.
so anyway, if we look at this first top group here, and they all have the same pattern, what you find is there's something kind of funny about data splitting that Ken Aho and I are looking at. And what happens is if you look at the R squared for the training set and the R squared for the validation set, intuition would tell you that you should get a smaller R squared for the validation set because the data was optimized to the training set. And if you look at row 3 and row 6, that's not true at all. And that's because more of the funny observations fell in the training set than the validation set. And as a matter of fact, if you look at those 6 sets of values, you find that there's a negative correlation between them. So this would tend to suggest that if I were to just do 6 data splitting exercises, I don't think I would be capturing what's going on here. But also, Ken and I are conjectured that if I did all possible data splits, that the R squared for the training set would just be R squared, and the R squared for the validation set would just be the R squared for leave one out cross validation. So as time has gone on, I've become more and more, I used to consider data splitting the gold standard and leave one out cross validation in AIC as approximations to data splitting. As time goes on, I'm moving away from the idea that data splitting is the gold standard and that leave one out cross validation and AIC are actually less work and more reliable. But I think there's an important point, the really important point I want to make, which one point I've made is that leave one out cross validation, data splitting, and AIC seem to do similar things. But when we were doing our research, we kind of found something that really people don't think about very much that I think could be relevant in health physics, the role of explanation versus prediction, which I think was first really laid out for me by Leo Breiman in the one of the papers, The Two Cultures, that I have referenced. It turns out that it depends on what you're trying to do, what you should be doing. The big AIC-BIC debate is about whether you're seeking prediction or explanation. AIC is designed to come up with the model that's best for prediction and does not assume any of the models are correct. It follows George Box's tenet that all models are wrong, but some are useful. And that's why I said it was important that I state what my objective was at the very beginning. Using data splitting and AIC and leave one out cross-validation were great when you're trying to come up with best predictions. However, if you believe one of your models is correct, then BIC will, with sample size goes to infinity, it will identify the correct model. And so if your purpose is prediction, you should be living in the AIC world. If your purpose is explanation and what really is happening, you should be living in the BIC world or the Bayesian world as well. That actually BIC matches up with Bayesian approaches. So I think the moral is something people may not think about very much. The best approach for theoretical understanding and the best approach for practical applications are often different. For example, it's possible that the model you're trying to build to really understand what's going on inside the body and the model you're trying to build to help the next person who shows up with radiation exposure may not be the same model in the short run, especially. So that's kind of something that might help understand where AIC and BIC fall. And then finally, these are just some references, including the two about the equivalence between AIC and leave one out cross-validation. So.
Any, better unmute my mic. Any questions on that?
Can you hear me?
Chris leads this nuclear innovation company.
May I ask a question?
Yes, please.
In my previous experience, I also tried to do a model fitting, and there we said, okay, we make differences between variables that are fixed for each observation and variables that are depending on the subject. So basically, let's say age or gender, and you group them. Is that important for this selection of which parameter to optimize?
Well, if you're doing general model selection, I'm not really thinking about the compartment models right now, just general model selection. Yeah, I mean, the idea here is as you add variables, you're adding complexity. So it increases P, so you're getting penalized for complexity and you're getting rewarded for fit. And so just adding variables, it just naturally, whether you're using leave one out cross-validation, data splitting, or AIC, all of those techniques are going to do the same thing. If you add a variable, it's going to have a penalty effect, and because you're adding complexity, and it's going to have a fitting effect. And you're only going to adopt variables if you get your money's worth for adding an additional variable. And even though it's not so obvious in the case of leave one out cross-validation or data splitting, there's math shenanigans I can do to show you that they're doing the same thing. They're penalizing you for adding a variable and they're rewarding you for fitting the data better.
Okay, thank you for this explanation.
Can you hear me?
Yeah.
Okay, good. Yeah. Coming from a physics perspective, I always wonder why you're not using the nomenclature of chi-squared. So I'm going to make a little comment here. From physics, or let's go back to the thing that is important, as I see it, the really important thing that we have is the ability to do Markov chain Monte Carlo to computationally create the posterior distribution. And that goes back to physics and a 1953 paper. I've heard it referred to as the most important paper that ever came out of Los Alamos. And in that paper, it was looking at statistical mechanics, and the thing was the energy of the system, and the probability is e to the minus energy over kT. That's the, and the correspondence is the likelihood function, which is e to the minus chi-squared over 2. So energy and chi-squared kind of go together, and they also go along with likelihood function. So in what we're doing, we need a likelihood function, we need a prior, and so, you know, fitting a good fit means that the likelihood is larger, which means chi-squared is smaller. And for the housing, your example of house prices, it seems like it would be helpful to go back to the chi-squared approach. You know, you say you create a chi-squared, a likelihood function for the price of the house. So it could be a normal likelihood function, or it could be a log normal or something like that. And so chi-squared is the summation, you know, you're calling the residuals, yeah. It would be the price minus the predicted price squared divided by some uncertainty. And so that the sum of that over all the data points, that's your chi-squared. And in this case, it's a linear model. The parameters of the model enter in linearly. So to minimize chi-squared, you just have to solve linear equations. It could be done on a spreadsheet. And then there are these, you know, that chi-squared, in a linear model, chi-squared, the minimum chi-squared, if you have a large data set, is the number of data points minus the number of parameters. And so you can set your, well, I mean, if you're comparing one model to the other, you just look at chi-squared. But I don't know, it seems like, you know, this goes back way back. And I'm wondering why you're not mentioning that approach.
Well, that approach isn't used much in statistics, but I think mathematical transformations would be pretty easy to equate the two. I mean, all you're really doing in this case, you're talking about a transformation of the likelihood, but you know, the likelihood is in the center of AIC. So it's just simply doing the same mathematical transformation. From that point of view, what you're really saying is, as you fit a more complex model, you get a better log likelihood as you add variables. So there must be a penalty there in order to balance that out. And you're simply saying, hey, the likelihood is going to be larger, so the negative likelihood is going to be smaller. So we're going to just add a penalty. And then you can take that thing and look at it as negative 2 times the log likelihood and just then transform it to however you're using the likelihoods in any context. So in other words, I think I could, like in a couple hours, come up with a chi-square version of everything I'm talking about. It's just not traditionally how statisticians concern themselves. I will say one thing, as I've noticed when people talk about chi-square, one concern I've had when people do a chi-square approach is often they take their chi-square and divide by n instead of dividing it by n minus p, which really I think is critical. It gets at this overfitting issue again, that when you have a large number of estimated parameters, there's a big difference between chi-squared divided by n and chi-squared divided by n minus p. But I'm pretty sure if I saw that paper within a couple hours, I could give kind of a chi-square version of this whole presentation, and it would just, follow along the same lines. It's just in different disciplines, people use, have a different technique, but it's pretty much a simple mapping, I think.
Yeah, one more thing about okay, so P is the number of parameters. I wasn't sure about that because it didn't seem to enter in right correctly because let's go back to just the basic physics approach to it, that you would take chi-squared per degree of freedom for a linear model. And so you take, divide by the number of data points minus the number of parameters. So when the number of parameters equals the number of the data points in a linear model, you can fit every point exactly, and chi-squared will be 0. That's not, well, when you go into a Bayesian or probabilistic approach, the number of parameters is not so important. You could have twice as many parameters as data points, and the average, the posterior average of chi-squared is going to not do anything strange. It'll be about 1, it'll be 1 actually per data point. So there's nothing, that would be a justification for dividing by the number of data points because you're referring not to the minimum value of chi-squared, but to the posterior average value of chi-squared. So, and what I was looking at, I wasn't sure what your parameter P was, but it seems like you had minus 2 log likelihood, and then you had 2P. I don't know. It seems like we're really talking about the number of data points, the number of degrees of freedom, the number of data points minus the number of parameters, and the posterior average of chi-squared is equal to the minimum value plus the number of parameters. So I think I'm getting that right. Anyway, okay, that's all I need to say about that.
Well, what I would say, just for a clarification, P is not the number of parameters. It's the number of parameters maximized by maximum likelihood. So it's the number of parameters that are fitted optimally by the data. If you have parameters that you have that are fixed, they don't play a role at all.
Yeah, that's understood. Yeah, it's the variable parameters are the problem.
But what I would also say is that if you, in the context I'm thinking of, if you get a perfect fit, then you have chi-square divided by n minus p. So chi-square is 0 and n minus p is 0. So actually that's an indeterminate form. It's not, so actually that's an undefined, an ill-defined quantity, not a perfect fit or anything like that.
Yeah. The point I'm making here, I'm distinguishing the minimum value of chi-squared as you vary all your variable parameters, and the posterior average, in other words, the chain average of chi-squared. And no matter how many parameters, for a linear problem, you can have, you know, many parameters, and the chain average of chi-squared will be 1 per data point. So that would be the reason for dividing by the number of data points. Is we referring to the chain average of chi-squared and not the minimum. And in many problems, it's not that. In nonlinear problems, there's not really a huge difference between the minimum chi-squared and the chain average in practice and the kind of stuff that we've been looking at.
Yeah, what I would say though is that if you are using this Bayesian approach, then BIC is theoretically going to do something very similar to that Bayesian approach. I have the paper I have at the end of the PowerPoint, Cass and Raftery, that actually explains the relationship between the Bayesian hypothesis testing and BIC, which are considered very similar. Although I haven't really looked at that as closely.
Yeah, I mean, we're basically talking about using chi-squared, but then the question of hypothesis testing. See, I mean, if you look at conditional probability rules, you can write down the formula for the probability of a hypothesis given the data, one hypothesis versus another. And the problem is it's the posterior average. No, I mean, it's not the posterior average, it's the prior average of the likelihood function, which tends to be prior dependent. So, you know, the question is, even though way back, in fact, at Los Alamos, we were using, in our dosimetry, we're using hypothesis testing, and just straightforward Bayesian. And so whether a person had an intake or not was based on probably the hypothesis that they had an intake just doing the math in a straightforward way. And we dropped that after a while. But I mean, it's basically, it works. And then it's always questionable, and maybe John Klump, I hope he's there, will comment on this, but the prior dependence of that is confusing, and it people don't want things to depend on the prior. But John, do you have anything to say about that?
Can you hear me?
Yes.
Great. Well, you know, we've got our questions about how to do this in a Bayesian perspective, and and I think maybe we should probably talk about those separately because they're at best tangential to the talk you gave. But yeah, you know, certainly, if you consider your prior and likelihood combination your model, and you have an uninformative prior, then your model is useless. It's going to give it, you know, the evidence integral is going to look terrible against data. And so, you know, data splitting is essentially the proposal that I put forth for how to get around that. But to comment on the AIC and your presentation, I don't want to call it a criticism because it's a problem, but I think it's my problem, not the AIC's problem, of actual implementation. That to get the right answer, you have to determine P. And, you know, that's fine on kind of dummy problems, homework problems where, you know, it's given to you. But for, you know, especially biokinetic models where, you know, the parameters are always extremely correlated. You know, the rate into a compartment is highly correlated with the transfer rate out of a compartment, for example. You know, getting the right value for P is, well, I honestly, I don't really know how to do it. But I can do leave one out cross validation, no problem at all, right? And so it seems like if they give me the same answer, then leave one out cross validation is going to be much more reliable in terms of giving me the right answer. But the other comment I wanted to make was that I thought it was really surprising, your result that leave one out is superior to data splitting. Just intuitively, I would think leave two out cross validation would almost have to be superior for a fixed number of data points, provided that number was not very, very small, than leave one out. So I was hoping you could talk a little bit more about about the details of that result and why you think that might be the case.
Well, it's kind of interesting. It is extremely counterintuitive that leave one out cross validation could be at all comparable to data splitting. But data splitting just has some very peculiar things going on with it that are surprising and counterintuitive that give me pause. I mean, the bottom line is, if I want to do data splitting, well, I'll try and get at two different things. If I want to do data splitting, then what happens is that I have to do a lot of different data splitting to take into account this negative correlation between the fit of the training set and the validation set. Now, as far as leave two out versus leave one out, that actually gets very complicated, because you might say, well, leave two outs better than leave one out, and leave three outs better than leave two out. Part of it is we've done a lot of theory on leave one out cross validation, but it's kind of funny because it's been shown that if you do small leave out cross validation, it approximates AIC. And if you do huge leave one out cross validations, it approximates BIC. So there's kind of some kind of funny continuum. There's some kind of funny continuum thing going on there that I don't think anyone understands yet. So there's a lot of weird stuff going on with cross validation. I guess what I would say is, I trust leave one out cross validation. We know a lot of theory behind it, and I think it's reliable. And leave two out might make more sense, but as you leave more and more out in the cross validation, it's actually changing the properties and what you're trying to optimize versus in terms of this prediction versus explanation. So I'd say there's just a lot that's not understood about data splitting and cross validation at this time.
Dwayne, John had mentioned something about trying to determine the value of P, and that being difficult in some of the experimental work. Can you address that a little bit?
Yeah, so regardless of these correlations, which happen in a lot of data sets, that betas and regression are correlated and stuff, we pretty much consider each thing you try and optimize, each thing that's being optimized rather than at a fixed value, as going into P. Now, one thing you could do, what anyone can do, is you can just simply, for a time, use leave one out cross validation and use AIC and say, hey, are they even getting different results? If they're getting the same results over and over again, then this correlation between the transfer rates is not playing a role. That it seems, I mean, it isn't really impacting the fitting. If leave one out cross validation and AIC are getting the same results, then it's either a problem for both or not a problem for either.
Does that help, John?
A bit, but it also kind of kicks me back to where I was starting, which was, leave one out cross validation will give me the definitive answer anyway. So why do anything else?
Well, I would say some of what I'm showing in that article, some of what I'm saying is research Ken and I still have to do, but I did a lot of data splitting and a lot of AIC and a lot of leave one out cross validation for my time series book I wrote. And over time, I've just become more comfortable. I consider AIC leave one out cross validation somewhat interchangeable. If you're going to do one and I'm going to do the other, I don't care. But I'm finding data splitting, it's got some anomalous things going on with it that people don't realize that trouble me a little bit. I'll just say that right now, just my opinion. It can be a bit troubling, and it's a lot of work.
Hopefully at some point we can talk about maybe how to do this in our Bayesian context, because at least for the Lano group, that's what we're really worried about. We don't really worry all that much about the maximum likelihood estimate anyway. Our uncertainty is so large. We care about what that whole posterior function looks like in a lot of cases. So, but I don't want to talk about that for an hour right now.
Yeah, unfortunately, I just don't, off the top of my head, I don't know those links. I don't know what kind of data splitting type technique would be connected to Bayesian approach right now. I just don't know that off the top of my head.
Tony, did you have a question? It looks like you were kind of in batter up circle.
I think he's muted.
I'm not getting your volume at all, Tony.
Sorry about that.
Oh.
Put myself on mute. Yeah, thanks for an interesting presentation, Dr. Terryberry. I think it's particularly timely to show that even when using simulated data, the perils of modeling into the uncertainty on the estimates, you know, that as you're increasing the p-value, there were changes in the model fit that didn't reflect the true data that you'd started off with, and it's always sobering to look at this. The temptation is always to follow this down. The thing I would say is that on your AIC values, I would perhaps stop at 7, a p-value of 7, because the AIC didn't drop significantly below that, but that's a debatable point. The thing I would mention by way of a comment about residuals is that looking at residuals can tell you other things when you're model building. In particular, plotting the residuals against the values can tell you something about the underlying structure of the error model, which you won't get from a gross metric of the fit like a chi-squared test. So that's often why you would use residuals in model building. And as you say, there's a difference between looking at explanatory models and looking at trying to build a model that predicts well. And I think these are, again, very valid points. And it goes back to the fundamental statistics. Another point I'd come out with data splitting is it's as old as statistics itself, in that the only perfect statistics are when you have the entire population for whatever it is you have under study. And the problem we have with real world statistics is getting a representative sample population which will be predictive. And this can often be, as you said, the problem with data splitting is splitting the data in such a way that you've truly got a subset which is representative of the wider population. And where perhaps leave one out for cross-validation works is that it's very good at picking up extreme outlier effects where you've got one point which is got a lot of leverage in the analysis. Yeah, that's all I wanted to say, so thanks again.
Yeah, just to second that first thing you said, you know, looking at residuals is important. I mean, one thing that we've noticed in some of the data sets we have is there's kind of a cluster of animals that fit the data almost perfectly, and then kind of a cluster that fit horribly. And, you know, those clustering things would show up by examining the residuals themselves. You're seeing, you know, clusters of different sized residuals.
Are there any additional questions for Dr. Derryberry? Well, Tom, you're a co-host on this. Why don't we move forward with your presentation?
Okay, I just have to just share screen, right?
Yes.
Okay, so you should be seeing my iguana now.
Okay. The iguana is being seen.
Okay. And so here's my talk. And next week, I thought it was important to go through basically where am I coming from on this, because I think your background and your experiences influences the questions you ask and what you're interested in quite a bit. I did what I'm going to call a regulatory internal dosimetrist for about 25 years. And so that was at Savannah River site. And that's somebody who does internal dosimetry to demonstrate compliance with the regulations. And so that's pretty much what that is. Since then, I've been doing what I call a compensatory internal dosimetrist. So that's about the last 15 years. And that's for the EU ICPA project, working for MJW. And that's working more towards doing internal dosimetry to make correct compensation decisions. And so it's an entirely different animal than the regulatory aspect. School, again, some time ago, I had a kind of a classical background in health physics. And then more recently, about the last 10 years, I've been taking classes and so forth at University of South Carolina in statistics in the biostat department. And I just finished all my classes and I'm trying to come up with a dissertation topic. And so this talk kind of leads through the background of the thought process to basically the question, you know, in quotes, that I'll try to address in my dissertation. And so it just as an overview, it just define what biokinetic models are. What I'm talking about is that basically the interconnected compartments, and we model the movement of a simulated radioactive material between the compartments, deterministic first order kinetics, and we want to describe the uptake of material into the body, and then the amount in each compartment, and then the rate of excretion. And so what I'm interested in doing is developing some methodologies that allow the modeler, and by modeler I mean the researcher developing the biokinetic model that is eventually published, to present physiologically realistic probability distributions for the parameters in the biokinetic model. And that these will incorporate basically all the prior knowledge of the modeler, the data that they have available, and account for dependencies among the parameters and account for variation in the population. And so given this will allow the practitioner of these models, so me as the internal dosimetrist, I'll be able to form evaluations that are customized to some extent to the individual and start talking about, for example, uncertainties in some of the quantities I'm trying to calculate. So again, I'm going to start with just basically linear regression and work my way up to a full Bayesian analysis. Before I move on, I need to acknowledge Guthrie, and again, I call him his Bayesian co-conspirators at LANL, past and present. He's been working on this for many years, and he's a big advocate of using Bayesian methods. I think it is clearly the way to deal with the issues that we're faced in developing and using these models. And I think he's done a lot to advance the science. And he kind of got me interested in this back in '97. We had a DOE workshop on Bayesian statistics, and we had some discussions there, and it was a very interesting workshop. Anyway, thank you, Guthrie, for all your good work. I'm going to start off with, this is the inverse problem, where basically the researcher takes all the available data and biological knowledge, they apply simplifying assumptions, and they developed an idealized compartmental model. And I emphasize this, it's very important. It's adequate for the task at hand, because you can never develop a model that basically accounts for every possible aspect of the system you're modeling, or else you'd be dealing with reality and there's no simplification to it. As Dr. Derryberry said, all models are wrong, but some are useful. He quoted George Fox. And this is a very complicated process. It requires considerable experience, expertise and judgment. And I think I will refer several times in this talk to Dr. Leggett at Oak Ridge. I've gone to talk to him a couple times, and I think he's a perfect example of somebody who's just spent decades doing this type of modeling, and he's published a lot of biokinetic models that are in the ICRP guidance and so forth. So again, I'll mention him several times, but it's with awe and admiration that I do so. We're going to talk about the iodine biokinetic model. Again, iodine is an essential element. It's concentrated in the thyroid. It's used to create thyroid hormones that regulate metabolism. And so discussion here revolves around a simple, and I say by today's standards, biokinetic model for the uptake of inorganic iodine. This is the Riggs iodine model. And I think in our first session, Idaho State session, Pam used the same model to play around with what she was doing. And I say by today's standards because I remember back when I first got into this, is that the Riggs model was very challenging in that it was a recycling model where everything else was basically there was no recycling, and it was very easy to solve it. And so again, that in the old days, it was sort of a challenge to work with it. And it's pretty much a toy example, and I think it's interesting and useful to illustrate some ideas and methods. Here's the Riggs iodine model. It's basically a structure, and as I quoted, it was first published in '52, and it was used all the way up until 2017 when it was superseded by the Leggett iodine model, which I'll also mention, and that's an ISRP 137. And so it had a very long life. It was very useful for what we were trying to do at the time. And I think you can see, again, I think most people are familiar with this. You have intake, goes to blood, goes to thyroid, goes to other tissues, and I'll define what these are. And again, it recycles and eventually goes to urine and feces. So, and these compartments are mathematical constructs. They don't really correspond exactly to any particular organ or tissue in the body. And if you look at the more recent models, it goes into almost a cellular level as far as the iodine metabolism. But blood represents the pool of inorganic iodine in the body. Thyroid represents the pool of organic iodine. These are the thyroid hormones in the body. I mean, overall thyroid, and other is the hormones in the rest of the body. Urine represents urinary excretion. Of course, feces is fecal excretion. So the forward problem, this is the problem that the practitioner deals with, is that we're given the structure of the biokinetic model, the values of all the parameters are given, and we want to know how does the system behave for different inputs, basically different intakes into it or uptakes. And at first glance, again, this is a relatively straightforward math problem. There's really no modeling here. There's nothing going on. But when you go to do this, the trick is deciding whether or not, again, this biokinetic model adequately describes the biological system of interest, whether its predictions are useful or not as far as trying to do whether we're doing a regulatory analysis or a compensatory analysis. These systems are all basically the movement of material in these compartmental systems is described by a system of first order differential equations with constant coefficients. And so basically what we're doing is given the rate of change in the contents and the initial contents at the time of intake, we want to solve the system for what are the compartmental contents at any time afterwards. And I go through this because this is, in the end, this will be important to the application of what I'm trying to do. And so there's our system of ordinary differential equations, and it basically talks about basically the rate of change in compartment 1, I think, which was the blood, and this is the amount leaving, and then this is the amounts coming in from the various compartments. Here are the rate constants for the iodine models. I have Riggs, I have ISRP 30, and ISRP 5668. And we go from the blood to the thyroid, and I have K12, and basically anything that's not specified here is equal to 0. So for example, the rate constant going from feces to thyroid is 0 because there's no transfer between those two compartments. And as a portent of things to come is that we're going to be particularly interested in these other to feces and other to blood transfer rate constants in here. And you can see that they were changed in the 5668 model versus the earlier models. And we're going to talk, again, these are of great interest here. And I just wanted to point out again, rigs drive these from basically looking at mass balances of iodine, stable iodine in a system that was in equilibrium. And I just go through an example here, talking about how we derive the thyroid to other transfer rate constant. I think it's kind of interesting, again, how they actually come up with these numbers. Intake retention fractions, which are basically the bread and butter of the regulatory internal dosimetrists, because we're going to evaluate bioassay data, come up with intakes, come up with doses, compare it to regulations, and decide if we have a problem or not. And so the fraction of the intake that's in a given collection of compartments at a given time, again, is returned to intake retention fraction, and it's little m at time t. And so computationally, this little m at time t is the sum of whatever compartments we think we're measuring with our bioassay method. And so if we're interested in thyroid count, which tells us how much iodine's in the thyroid, then we're interested in just compartment Q2. That's the thyroid, and so that's basically the ERF for it. But if for some reason we were doing whole body counting for iodine, radioiodine, we would have to sum up compartments 1, 2, and 3, and that would be the ERF for the whole body count. Okay, so this is again, a little example. This was at a facility I worked at, a researcher, and I just call her subject 0. Was working with radioiodine, doing some sort of synthesis, and had an intake. And so the bioassay method of choice here was a thyroid count, and we quantified the amount of iodine 125 in the thyroid by the radiation it emits. And so these were 37 thyroid counts over about 90 days. And I'm showing on the plot here, along with the 1 sigma measurement errors, measurement uncertainty. Here's a table of the data in case you want to go home and play with it. And we're going to talk about the least squares intake. And so this is, I think if you were to tally up all of the people doing internal dosimetry in the world at any particular time, I think the vast majority of them are going to be using this technique or some variant of it to estimate intakes and determine compliance. And so given that data, the best estimate of the iodine 125 intake is you make a regression of the bioassay data, big M, on the ERFs, little m, through the origin. So it has to go through 0. So in this regression equation, there is no intercept. The intercept is, you could say it's 0, but it's not 0, it's just not there. And so the slope of this is going to be beta, which will be the intake, and then this has the normally distributed regression errors. And when you go to do these regression errors, typically what you have to do is come up with some error model of how these regression errors are distributed. And so in this case, which is typical, we're going to talk about they're normally distributed. They have a mean of 0 about the regression line. And again, they're heteroskedastic, which means that each thyroid count has a different measurement error, different regression error. And so the standard way of handling this is we come up with basically a covariance matrix that talks about a matrix Q that we know up to some constant multiplier, sigma squared. And so this is what sigma is in the normal distribution. And a standard way of doing this is that we can go through and we can say, okay, this is basically, Q is going to be the gum measurement uncertainty squared. On its diagonal, it's 0 everywhere else, which means it's not correlated. Is there a question? Okay. So this is what it'll be. And so it's just basically it's sigma squared times each of the measurement uncertainties will go into the least squares equation. Okay. And so this is standard probably in physics class or math class, your stat class, you do this, is you set up your sum of squares. And this is the basically the chi-square statistic that Guthrie is talking about to minimize. And again, you go through and you differentiate this with respect to beta, which is the parameter of interest, set the result equal to 0 and solve for beta. And this gives you a closed form of solution that looks like something like this. And so when we plug the data in, we get about 1620 nanocurie intake. And again, notice that the sigma cancels out of this. It really doesn't play a role in if you're just estimating one parameter. Okay, and I typically do this just for didactic reasons, and this is what we're doing the regression about, is that we're regressing what we measure in the thyroid versus the ERF. And you get a straight line, looks like this, it goes through the origin, and you can see how the data points are scattered about it. The slope of that line is the intake. Okay, and the best fit of that regression line to the data can be achieved only by rotating that line around the origin. For example, you can't move this line straight up. It has to rotate left and right around 0. The pivot point is 0. Okay, changing the biokinetic model changes the ERFs. It changes the values down here. And again, for this, I would say, again, for the purpose we're using it for is that there's no significant lack of fit in this. The Riggs model appears to adequately describe the iodine biokinetics of that person. There's no problem with this. This is how we typically look at it, is that you plot the iodine burden versus time after intake. Note that this is a log scale, so this is a semi-log plot. And so on here, you also get a straight line, but the slope of that line, of course, is not beta. It's just the intake. So I changed the notation here is that this is what the intake is. The only time I'll use beta is when I'm actually looking at this plot, because that is the slope of the line. Okay, again, least squares, I think, again, is the workhorse of occupational internal dosimetry. Common modifications include you have different types of weights to deal with different types of non-constant regression errors. And one of the most popular options recently for this is you do a weighted least squares of log transform bioassay data in ERFs. And I think if you take a look in like IEA 37 and some of the Eurodose documents, and ICRP also, this is the way they're suggesting that you analyze the bioassay data with a basically transform, do a log-log transform, and then fit it through regression through the origin. We're going to be working on some methods, though, that you need something more powerful in order to deal with it. And so we're going to talk about maximum likelihood. And so basically what we're looking at here is to get the process that generates the bioassay data. You're going to model it with a normal probability density function. So this should be a pretty close representation of what a normal probability density function looks like. And so what it's saying is that the observed data, given the intake, the ERFs, the uncertainties, and that proportionality constant is equal to basically the normal curve evaluated at those parameters. Okay. So the likelihood is you just take basically for every bioassay result and you multiply this together, and then that's your likelihood function. And if you go through and find the maximum of that, that is your best estimate, your likelihood estimate, maximum likelihood estimate of the slope of the intake. And that may or may not sound complicated, but when you do it in practice for one parameter anyway, you just evaluate this function at every value of the observed bioassay data. You'll get a curve, looks like this. Of course, it's going to be a quadratic, and then I don't even need to do math on this. I can pick out where the maximum of this thing is right at the top, and I'm going to get somewhere real close to 1620. Okay. And if you use a normal likelihood, it gives you exactly the same answers as you'd have for intake with least squares with normally distributed regression errors. The one advantage over least squares that's of practical significance to most people is that it provides an elegant way of handling left-censored bioassay data. This was incorporated into the IMBA software. I think was one of the big selling points of it when it first came out, is it allowed you to deal with that. But it also offers a potential solution to a problem we frequently run into, is that the biokinetic model does not fit the observed data. This is subject 7, and I'll tell you where subject 7 came from a little later. And so this doesn't fit. Okay, there's evidence that the Riggs model does not adequately describe the iodine biokinetics of this person. So I think anybody who's ever done internal dosimetry runs into this problem. So it's like, what do you do? And I think what you do depends upon what are you trying to do. And so if you're a regulatory internal dosimetrist, you can just say, well, That's good enough for government work, and we can determine regulatory compliance. We're not over any regulatory limits based upon that data, and just move on and don't worry about it. If you're doing some sort of compensation calculation, you could say we're going to maximize, like we're going to make the line go through this upper point here, which will give us our maximum possible intake and dose, and so that will give us a bounding number we can use to make a compensation decision. Or you could say, well, I'm going to tweak parameters in the RIGS model, try to get a better fit. And of course, I think this last option is going to be more entertaining for us to look at, and so let's see where it takes us. Okay, so this is the inverse forward problem, I'll call it, or inward. I guess that's a contraction of it. And so the predictions of the biokinetic model don't agree with the observed data. We ask the question, how can we modify or tweak the biokinetic model to get better agreement? And so in other words, what we're asking is that we have, the inverse problem is knowledge to biokinetic model by an expert, and then the forward problem, the biokinetic model to the predictions by the practitioner. And so what we're asking for is feedback along this line, which isn't normally done. It's difficult to do. And so we want, basically for our particular case, what we're seeing to feedback to modify the model. So again, we've always been taught to do this with caution, that you have to, because we don't know, a practitioner, I don't know which parameters to tweak and by how much. I can change all kinds of different parameters. And just because I get a good fit doesn't mean I've changed the right parameters in the right way. Especially if you try to do this manually. We've already discussed that parameters are correlated, so you just can't change one parameter and leave all the others the same, because you're going to end up with unrealistic biokinetic models because of this correlation between the parameters. And the other thing is, you always risk overfitting, is that you keep changing parameters until you start fitting noise in the data and you're not just fitting the signal. And this is hard to do by hand. So undeterred, of course, I'm always undeterred, is let's take a maximum likelihood estimate of the intake and model parameters, because I can do that with maximum likelihood, which is why I went this direction. It's a better fit of the data. And so the rate constants, K, are treated as what are called hidden or latent variables to be estimated. And we don't actually observe these. We observe their effects on the ERFs compared to the bioassay data. And so basically we have 6, we have the intake and then the 5 rate constants that we're going to try to estimate by maximum likelihood. Okay. Let's see, I got a text. I was just checking. I didn't know if it was Liz or not. But the problem here is that if I had one dimension, I can basically do this by hand. I can pick out the maximum. But if you have a 6-dimensional likelihood, then it's much more difficult to do that. You can't do that by eye. You can't work in 6 dimensions. So you need some more powerful computational tools. And I just put a plug in for R. All the work I do is pretty much in the R scripting programming language. I give you some specifications for it here. And I think the key things is that it's free and open source. So all the calculations I do in this slide were done in R. I could send you the script. You could run it and reproduce every plot, every number that I have in this presentation. Very easy for you to do. It's created and maintained by the R Foundation, which is statisticians. They're not bean counters. And so it really has, if there's a cutting edge technique that comes out, it comes out in R first. That's where statisticians work. And you can get over almost 16,000 packages which add on additional functionality to R written by other people. And I'm going to be talking about 2 of those that I've been using. And again, it runs on Linux, Mac, and Windows. When I go through and do maximum likelihood estimation on that model, we have what I have on the first is the parameter, which is beta, which is the intake, and each of the rate constants. This is blood to thyroid, blood to urine, other to feces, other to blood, and then thyroid to other. The RIGS parameters, and then these are the estimates that I came up with. We have the point estimate, the standard error, and then the estimate divided by the standard error, or the z-score, we'll call it.
So Tom, just a question. In my mind, you're using that subject number 7 and his data?
No, this is 0. I'm sorry.
Okay.
This is 0. The 7, I'll show you a little later, but basically I used subject 0 to generate simulated data sets for other subjects.
Okay.
So 7 was one of the simulations. And I'll show you how I did the simulations in a slide here. It's just straightforward, but it's just I wanted to work with the real person. So again, what this is telling you, you can take a look at the z-score, and if this is a large number, then that means I'm pretty confident in the result. And you can see here again the errors in the estimate are much smaller than the error itself. And so the key things to look at here is I'm pretty much getting back the rigs for here and here and here. But these two characters, I mean, this was a change of like 200. So I'm very confident that Riggs was off by a factor of 200 is what I'm saying. And so when you see things like this, is you say, okay, there's something going on here. I may have a problem numerically. For these two rate constants, I'm having difficulties numerically doing this. And so we need to look a little closer at that. And the problem that you run into is this non-identifiable model issue, is that you can go through and check for a model. A non-identifiable model is a model that no matter what you change these to, they can take on very different parameters, values, and you get the same answer. So basically you can't come up with a unique solution to the system just given thyroid data. And that's what the case is for the Riggs model here, is you can't do this. And you can check for that, is that from the Riggs model, you simulate 500 perfect thyroid burdens over 90 days. And then you go back and use the Riggs model to fit it by maximum likelihood. And you ask the question, did I get something back that resembled the Riggs model parameters that I put into it? And I say, yep, yeah, there's some problems with this, because if we look at these two, I'm getting back exactly the same numbers I put into it, but I'm not very certain. I'm not very certain that I have the right numbers here. They have a very large error. I mean, compare the size of this error to the size of this estimate. And so even given perfect data, the problem here is I can't estimate these parameters precisely. There's really no unique solution to this. And so that's the problem with trying to use math. And this is a simple 5-compartment model. Can you imagine trying to do this with a 20-compartment model? Again, most of these things are going to be non-identifiable if you try to approach them this way. You're not going to be able to get unique answers. Okay, so again, in theory, this should have worked. It looked pretty good, but given only thyroid counts, again, it depends what data you have. If we had urine data or blood data, then we probably could have identified all of the rate constants in this model, but only given thyroid count data, the Riggs model is non-identifiable. Again, we can't come up with unique solutions. And again, unconstrained maximum likelihood can give you physiologically unrealistic estimates of these parameters for that reason. It gives you normally distributed parameter estimates for the uncertainties. And this is the big thing right here, again, is that we know a lot about iodine metabolism that is not being incorporated into this analysis. There's just tons, and I'll talk about this some more, just a lot of information that we could bring to bear to help us to come up with a unique solution. So again, the obvious solution to this, and I think every talk on Bayesian statistics that has ever been, has this one photograph of Reverend Bayes, or picture, because it's the only one I think that exists of him. So what we want to do is bring additional information about these rate constants that is not from the current experiment into the calculation. And so a non-Bayesian would say, we're going to regularize the estimate of these rate constants by using prior information. And so again, the natural way to do this is a Bayesian analysis. And here we go through and just basically talk about the posterior distribution, again, that Guthrie was talking about. So the distribution of the intake and the rate constants, given the bioassay data, the uncertainties, and the proportionality constant for the regression error, it's going to be proportional to the likelihood, which we've already discussed. But we put in these additional probability distributions for the intake and then for each of the 5 rate constants. And what we're going to do is we're going to incorporate what our prior knowledge, what information we had about the intake and the rate constants before we looked at this data. And again, this is not a proper PDF, but if we're only interested in point estimates of these parameters, we can use our optimizer that we used before. which is the program that goes through and finds the maxima of this six-dimensional log normal distributions. Basically go through, and these are called maximum a posteriori or map estimates. And so I wanted to do is go through and say, okay, let's come up with some prior distributions and go ahead and calculate the map estimates and see how they work out. So priors, we talked about priors, I think, a lot in this series of presentations, but there's two types in particular I want to talk about, is the vague, uninformative, or flat priors. And these really give very little information about the distribution of the parameter in interest. And these are used, people will say, again, allows the data to speak for itself, and you don't put these overly restrictive priors on things. And on the other end, the extreme, you can have informative priors, and it basically brings everything that you know about the parameters into the calculation. And so, again, the priors that you use depend on really what you want to know beforehand and what you want to learn about the system. And what I'm going to focus primarily on here are informative priors. They bring a lot of information that's outside of the experiment that you're looking at into the calculation. So this is a SWAG, which I think is a formal term. It's scientific wild ass guess. And so this is just me playing with this. And one of the arguments I'm going to make is that I shouldn't be doing this. I need to have somebody who knows what they're doing come up with these informative priors. But this is the SWAG for purposes of this talk, informative log normal prior for K12. The blue lines are the 95% probability interval for this. Again, it's log normally distributed. We use log normal distributions primarily in here in order, basically, it prevents you having, you have all non-negative estimates, because you can't have negative estimates of the rate constant. I mean, you can theoretically get 0, but you're not going to get a negative. So that's a 95% confidence interval. We have the geometric mean and the geometric standard deviation, which most people are going to be more familiar with than the log mean and log standard deviation. So again, all the rate constants I'm going to assign with basically priors with a GM equal to the Riggs rate constants and a GSD of 1.25. So this gives us a 95% interval, about 1.5 times and divide the point estimate, the geometric mean. Again, these are you know, I don't think they're overly informative, but they are not flat. They are informative priors. So when you go through and run the map estimate, and so we're basically finding the maxima of this function here. Again, I'm not trying to do a full Bayesian analysis. I just want to find what are the maxima of this posterior distribution. And I can use the same software that I used before. Again, this looks much better. You'll see that I'm getting back stuff for these two rate constants that resembles Riggs, but I'm pretty confident too. Okay, the errors are quite small, and so this is really giving me back numbers that don't alarm me as far as what's going on. I can also run this on the perfect data. I didn't show it because it also comes back and gives you some good results back. There's no problems with it. I wanted to show this. This is the correlation matrix from those map estimates, and almost all these parameters, again, are highly correlated. And so these are, for example, the blood to urine, of course, is going to be pretty highly correlated with what that's itself, but these other parameters. So blood to urine, other. So you can see how everything is correlated here. So again, you can't just go in and change one of these willy-nilly if you're trying to tweak this by hand. Well, and I have some better plots of this later when we do the full Bayesian analysis. Okay, so the point of this is that reasonably informative priors, again, are very helpful for, say, calming down the sparse and noisy bioassay data and allow you to get good map point estimates of these rate constants for a specific person. And the trick of this, of course, is to get reasonably informative priors from someone who knows what they're doing, not Tom LeBone, but Dr. Leggett. So, or if he was doing his iodine model, or Dr. Riggs was here, have them say, hey, this is how this should be changing. This is how confident we are of this. And I'm going to talk more about this shortly because this is really the crux of the whole talk. This is probably the end of the road for regulatory internal dosimetrists because, again, we're only interested in the point estimates because anything else like uncertainties or anything like that really have no role in the regulations. if you get a speeding ticket, the officer doesn't quote basically the confidence interval for how fast were you traveling. It's basically, he says you're over it, and so you get a ticket. And so the regulation is worked that way also. There's no discussion of what regulatory role do uncertainties in any of these parameters play. However, the compensatory internal dosimetrist, again, we're looking for something more. We'd like to know the uncertainty in the model parameters ultimately that can be propagated to the uncertainty and the probability of causation that's used to make the compensation decision. It becomes more of a probabilistic question. It's not a basically deterministic yes/no question as it is in the regulations. So for that, you have to go to the full Bayesian model, and so we have the same terms as the we had in the map, but again, we have this really ugly integral in the bottom here, and this is a for any particular problem, this is a constant. This is a constant of integration that turns this proportionality into an equality. So it makes the posterior into a proper probability density function. And if you have a proper probability density function, you can calculate things like the mean, standard deviation, and so forth, things that you're interested in. Okay. So we need to be able to do this calculation, and again, we need some realistic informative priors. That integral, for any practical problem of interest, is going to be intractable by conventional numeric and analytic methods, and so this is where we use specialized methods like Markov chain Monte Carlo, which has been discussed. And so this is obtained samples directly from the posterior distribution, and again, from those samples, we can calculate things like mean, standard deviations that are of interest to us. So to do these MCMC calculations, you need some specialized software, and you can either write your own. It's not too hard to do, but it depends, or you can use off-the-shelf packages. Currently, what I'm working with are two different off-the-shelf MCMC packages, Stan and Nimble. Stan is named after Stanislaw Ulam. The picture here was a mathematician in the Manhattan Project. Nimble, I don't know who it's named after, but I'm pretty sure it's not Jack B. Nimble, which is the diagram here. The calculations in the presentation were all done with Stan. Okay. These are both free open source software packages that run on the R platform, again, which is another good reason to work with R. So this is what is called the Bayesian crank. One of the beauties of the Bayesian method is if you've done frequentist statistics, it's like a cookbook. There's a different approach basically for doing everything. For the Bayesian method, we give a prior for the error, prior for the biokinetic model, prior for the intakes. We have our data. This plugs into the likelihood. You run it through your MCMC calculation, you get a posterior distribution, and then you summarize and get your answers. And this is called, again, turning the Bayesian crank. Just about every problem that you can run into can be fit into something that looks like this. So again, using the heteroscedastic error model, this is the likelihood. The prior on the intake, everything has to have a prior in order for you to turn the crank. I am making this a vague log normal. I don't really know what this is, and so basically it's a GM of 2000 and a geometric standard deviation of 3. Again, these log normal priors ensure that the posterior distributions are strictly non-negative, and so they're very common to use them. These are the swag informative priors, as I discussed before, for each of the rate constants. We have the Riggs constant, and then this geometric standard deviation of 1.25 that apply to all of them. Okay, so typically you run this 5,000 samples in 5 separate chains, and it's basically five different starting points in the process, and so you can compare checking for convergence. And I'll talk about that in a minute. So this is 25,000 samples from the posterior distribution, and each of these we get a point estimate and some standard errors for it, and we can see compare these to what we were getting from the map estimates. Again, they're not that far apart. So again, but if you're only looking for point estimates, you wouldn't go through this anyway. You would probably just stick with the map estimates. And this is, it's called a SPLOM. It's the log of these rate constants. On the diagonal, we have the distribution on log scale. And so you can see these are log normally distributed. They went in as log normally distributed and they're coming out, which doesn't, which makes sense. Practically all of these are correlated. The 3 stars means that it thinks that it's correlated. There's really only 2 of them that they're uncorrelated. And in some of these, like here, you can actually see the fact, we have this, kind of a diagonal cloud, a tilt to it, that we have these correlations going on. And so this goes through and basically tries to estimate those correlations. This is the mean of the intake posterior distribution, and it was estimated at 1757. And so what, we got 1620, I think, out of the first least squares. And so this is the credible interval, you see 1218 to 2589. And you can see that it's log normally distributed pretty much also. It looks that way. I didn't try to go fit it. When you do MCMC, for any finite number of samples that you draw from posterior distribution, you're never going to know whether the MCMC has converged to the right answer. This is a inherent problem in this. The theory is there to say if you take an infinite number of samples, you will get the right answer. But again, people don't typically take infinite number of samples. So you have to do a lot of diagnostics every time you run this to try to judge the quality of the analysis. And these are trace plots or caterpillar plots, the type of thing you would look at that says, yes, this is mixing well, this is coming up with good estimates for these rate constants. But again, you have to look at all these things, and there's quite a bit of different diagnostics available to do this. The runtime to do that 5 times 5,000 samples took about 18 minutes on a capable workstation. So it was a pretty good workstation I had. It was 8 physical cores, 16 with hyperthreading. It was an i7. Again, it worked. And you can run, the nice thing about the Bayesian analysis, you can run them separately. You can run each of these chains on a different core, and so you can multitask it. Again, I haven't run the 20 compartment Leggett model yet, which is right here. But again, it would probably be good to have a lot of coffee and maybe a supercomputing cluster to do that. In contrast, that map estimate, where I was only interested in the point estimates, took 11 seconds to calculate. So again, if you're only interested in point estimates, then you don't need to go through this whole thing to basically figure out that constant of integration in Bayes' formula there. This is from Dunning. I think this reference was mentioned also in the series so far, and that's here. What he talks about is the distribution of thyroid retention half-lives in the population. And so he pretty much comes up with a log normal distribution. And from that log normal distribution, I went through using the characteristics of the thyroid count data I had, and I generated 10 different people about how the next person coming in, if they had the same sort of intake, how their thyroid burden versus time would look. And so the one in red is subject 0. I don't know which one subject 7 is, but it's not this guy down here. It's one of these in the bulk here. And so what this is pointing out is that, we're doing a lot of estimates and it's for a person, but there's a lot of variability in the population that you also need to try to take into account. And you can different ways of doing that, but that's one of the things I wanted to look at. This is the what I'm calling the idea of a can prior, and I asked around to I'll tell you what I'm going to do. It's just a can prior is a prior. It's just it's a prior that used to be a posterior. So it's a posterior from the previous calculation becomes the prior for the new calculation. And rather than say that big long word, I wanted to go ahead and give it a name of some sort. Canned is not, if you look it up, it's not a real word. It's just something I'm using for this talk. And so again, we're going to take the distribution of the posterior samples from the model development. So Dr. Leggett goes through, he generates this, this model, and he comes up and he has posterior distributions of all of his parameters. And so we want to go through and approximate those posterior distributions in some sort of compact form, for example, multivariate log normal. And that this canned prior, again, it's going to capture the distributions of parameters for an individual level, this covariance structure between the parameters at an individual level, and also the variation of these parameter distributions at a population level. And so again, a summary of these posterior distributions then becomes the informative realistic prior distributions we can use for doing Bayesian analyses on a person or map estimates on a person. So the application, I'll go through it, goes something like this. So the modeler, Dr. Leggett, he uses a Bayesian analysis to utilize all available data, prior knowledge, and expert swags, basically to come up with his model. Again, you can also use this for selection of model structure, which Dr. Derryberry was talking in the previous talk. I have to emphasize, I went back and looked at the 2010 Leggett iodine biokinetic model, and there's got to be at least 100 references in there of previous research he's looked at, and it would be really wonderful to somehow capture all of that, the years that he spent on that model, everything he looked at it, to condense it down into one canned prior distribution that could be basically used on the new calculation that you're going to do for a particular individual. So the idea here is that Dr. Leggett would publish these canned priors in a form, or have them in a form that can be published. So instead of getting a table of parameter estimates, you get all the parameters from this canned prior that you can then just use right into your new Bayesian or map calculation. And so as a practitioner, I would take that published canned prior, I generate my own map estimates or these posterior distributions, and really go everything I want and be confident I'm using the best priors available, and I'm not using these vague priors that really don't solve any of my problems. So the summary, again, the whole purpose of this, again, was for the practitioners to do more. As a practitioner, I'm being asked to do more, like customized dose estimates and uncertainty estimates. I need more information from the modelers. Is that I feel as practitioners, we should not be just coming up with flat and uninformative priors just to be able to turn the Bayesian crank. If we're going to do this, I need more help from the modeler. And again, one approach of doing that is having the modeler use these Bayesian methods to build and evaluate the biokinetic models. You summarize these posterior distributions in this canned prior form, and you publish it with the model. So this all led to, okay, what are you going to do for your research? And so what I wanted to do, and I probably have a couple of years before I run out of gas here, is basically fill in. There's a lot of statistical details in that canned prior that I need to work on and develop, and so you can come up with this in a form that's usable for these complex PBPK models we've been discussing. I think everybody who's ever done this has wanted to do something to speed up these calculations. You may not have caught on to it, but in the full Bayesian calculation for the MCMC, I did 25,000 samples, and for every one of those samples, I had to go back and reevaluate the system of differential equations. And everybody who's ever done this has tried to figure out a way of getting around stuff like that. And Guthrie and John could tell you about the ways that they're doing as far as coming up basically with libraries of models, and so they don't have to reevaluate those differential equations every time. But again, it's always an issue to do this. I'd like to work on making these calculations more accessible to modelers and practitioners. And so the other thing I'm looking into is coming up with perhaps an R package that would automate a lot of this or hide it from the practitioner. And Nimble is probably the platform that I would use to do that. And the final thing was there's just a bunch of really interesting things that I've seen along the way that I might look into or might not have time. But that's pretty much the research areas I was looking at. So again, questions, comments. Thank you for your attention.
Interesting. Any questions for Tom right now? I'm sure there are, but please.
So John and Guthrie are not going to let me out of here unscathed. So come on. Yeah.
Maybe if you unshare your screen, that would be good,
Okay.
so I can see who's out there.
Can you hear me?
Yes, Guthrie.
Okay, good. Yeah, thank you. I remember that workshop. That was fun. way back. Yeah, just one comment, and I think this is kind of important that we have to push for this. The question is like can priors versus publishing the data that the modeler used, specifically Richard Leggett getting the data that he uses. There's arguments one way and the other, you know, because the data goes back to the original experimental work, which is good. Data is independent, you know, right? It's just canned priors are a little bit different. It would be involve the prior that's assumed by the modeler. So it's got some assumptions in there beyond what the experimentalists that did the measurements, you know, thought was reasonable. So, and then it's also correlated, you know, you have this whole matrix thing. So I would argue just what we really should be doing is always publishing the data in our papers so other people can repeat the calculations.
I agree with that 100%. A lot of times, and I think as you know, which is the reason you're bringing this up, it's very difficult to get data. People don't want to share their data. They have all sorts of basically, you know, private information. You have to go through committees to, you know, at the school or the research facility to get it. And I think if you're going to publish a paper, you should publish the data with it. I mean, that's hard to come by. But I know you're interested in the data because you're a modeler, you're a researcher. You want to go do things with it. And I'm again coming more at the perspective is that I want, you know, Dr. Leggett to tell me what I need to do in order to do this right. So again, to condense not only the data, but all of his guidance, all the research he did, all of his professional opinions on these distributions of these parameters. And so again, I'm looking for more help from the person who's spending years developing these models to just give me more of that information. And how do you come up with a form, basically mathematically, that you can do that for the practitioner? And so again, it comes, what are you trying to do with it? In the, what's your goal? And I think that's a difference in perhaps, again, what we're trying to do, so.
I enjoyed the presentation. It's always fun to see something for the second time. So thanks. Because you sent me a draft of your dissertation proposal some time ago, and I gave it a careful read and learned a lot from it. So I thought it was really good. I won't repeat all of the comments that I sent you based on that, but one thing that really stands out when talking about models, when people talk about biokinetic models in general, that I think it's always really important to keep in mind is that there's kind of two categories of parameter optimization in my mind. There's the dose assessment category where the parameters that you're optimizing for your model are the parameters that are specific to a given intake, right? So a person inhaled some iodine, and you want to know how much, right? That's one of the parameters is the intake, but you're leaving parameters like transfer rates fixed, and in fact you leave them fixed even if the person doesn't have a thyroid, because you're trying to calculate a regulatory quantity, which is the risk to the average person who experienced an intake with these characteristics, with this intake, for example, in this solubility class. And then there's the problem of trying to fit transfer rates. But again, you've got to, it's sort of a similar thing. Do you want to figure out what the transfer rate is for your subject? Do I want to know what this individual's metabolism looks like? or do I want to know what the average metabolism of the population does? It just depends on the use. So, you know, the other difference is, as you mentioned, is that usually with intakes, with those types of parameters, often you're more concerned with point estimates because the regulators need a number. Whereas, you know, if you want to understand what's going on in the body,